All right, I'd like to look at a couple more of these constant acceleration problems in which we've got the acceleration being the acceleration due to gravity. In this next example, let's start out again with an initial velocity in the vertical direction of 50 meters per second. Then let's allow the mass to go to a maximum height, and then to come back down again, and then to continue to drop below the height from which it was released. So let's allow then for the fact that maybe this is on the edge of a building or something, and this is a 20-meter high building, and we want to know what the final velocity is just before it strikes the ground 20 meters below the height that it was released from. And so in a problem like this, we actually have two different displacement vectors. One brings us to the peak of the path, and the other brings us from the peak all the way down to minus 20. But by using head-to-tail addition, we can go from the tail of the first to the head of the second, and so we see that our net displacement vector is negative 20. Because this part going to the peak and this part coming back down, and we already figured out what this peak distance would be. It was 125 meters from a previous problem. But in this case, we don't really necessarily need to work with that if we don't want to. We can just use the fact that the net y displacement is negative 20. And so here we would define a positive direction as up. The acceleration due to gravity would be down, and that acceleration would be minus 10 meters per second squared. And so really now we have enough information to find v final. And the quickest way to do that, again, is to set up a table of knowns and unknowns. And we need to know 3 out of 5. So here we've got v initial equals plus 50 meters per second. And we're going up and back down, so this is our final point now. And so y would be negative 20 meters, and that's a vector. And then we also know the acceleration, a, that's minus 10 meters per second squared. So we've got 3 out of 5. That means we're in business. Our unknowns are v final and the time. Okay, and so if we want to proceed then to find v final, the velocity at this point where it's 20 meters below the height from which it is released, we can eliminate all the equations involving the time, check your list of those 4 equations. What you'll see is that the remaining equation is v final squared equals v initial squared plus 2ay. Okay. And so in this problem then, the acceleration and y are negative, so that this term is going to add to v naught. Now if y were 0, we'd be to here, and we'd have v final equals v initial. That would be plus or minus, so that would be negative 50. So if we just went to there, then the final velocity would equal the initial. But then now it's got time to pick up speed until it gets to minus 20. So that's going to add a value there, and that's going to make v final larger than v initial. And so if you make a minus sign error here, which would be an easy thing to do, maybe you only make one of these negative instead of both of them, then you'll know that that can't be right because v final will be less than v initial. So for this problem then, v final squared would be 50 meters per second squared plus 2 times minus 10 meters per second squared times minus 20 meters. Okay, so again, the negative signs cancel out, and so this is going to give us 2,500. I drop the units in the next step, plus, and then here we've got, what is this? 200 times 2 is 400. So that would be 2,900. So V final squared is equal to 2,900. Or V final is equal to plus or minus root of 2,900. In this case, the plus root has no meaning because clearly the mass is moving in the negative direction. And so this would be negative square root of 2,900. And that would give us 53.8 meters per second. Now, is this a reasonable answer? Well, it's more than 50. And so we know that in this 20-meter extra distance, it's had a little more time to pick up speed, but in the negative direction. So that doesn't prove that this answer is the right answer, but it indicates that it's in the right ballpark at least. It's a reasonable answer and is the solution to this problem. Okay, now if I also wanted to know what the time was, what if I were asked for the time first? Well, if I were asked for the time first and then V final, then I could go to something like y is equal to V0t plus 1/2 AT squared. I could solve that equation for the time, but it would involve the quadratic equation. So if I were asked for the time first, but I was still also asked for V final, I could just solve that problem first. And then I would know what the time was. And from that point, I would be able then to use a different equation to solve for the time. Say, for example, the first equation, V final equals V initial plus AT. That one's much simpler algebraically, and I think the way to go in terms of just saving yourself a little bit of trouble with the algebra. And so T then would be V final minus V initial over A. V final we already have. That's been put over here in the known column and is minus 53.8 minus V initial 50 meters per second divided by A, which is minus 10. So that gives us minus 103.8 over minus 10. And that gives us, what's that? Move the decimal place over 1. That would be 10.38 seconds. So that would be the time. Is that a reasonable value for the time? Well, we know that from a previous example, if we start with an initial velocity of 50, we go 40, 30, 20, 10, 0. That's 5 seconds. And then 10, 20, 30, 40, 50. That's 5 seconds. So that's 10 seconds to there. Then a little more time to get to the 20-meter point below the height that it's released. So this is a little more than 10 seconds. And so that's a reasonable answer then for the time as well. Okay, so those are the kinds of problems that you can deal with in which you can just essentially eliminate the unknown that's not asked for and solve for your desired result. But what I wanted to do next was to take a look at a problem where we don't have the initial velocity. And let's see how that would change our result. This is a special kind of a problem. It might seem like, well, that's just one of the unknowns and it wasn't given, so how does that make it special? Well, let's start out with maybe it's a grasshopper. that jumps with an initial velocity of v naught that's not given, and the grasshopper jumps to a height of 2 meters. Okay? And so from this information then, let's find the amount of time that it takes before the grasshopper lands back on the ground. So this is up and then back down again. All right, so I have a choice here of ways that I could handle this problem. I could start out and figure out the time to the peak and then double that, because I know that however long it takes to get up is going to be equal to the amount of time that it takes to get back down by symmetry. But if I do that, I'm going to need to set up a table of knowns and unknowns. I usually like to define the positive direction in the initial direction of motion. The acceleration due to gravity is minus 10 meters per second squared. And the final velocity to the peak is just 0. Okay? So here we know that the maximum height, y, is 2 meters. So I'm drawing all these vector quantities in. I've got a final velocity of 0 and acceleration of minus 10. So it looks like we should be okay because we know 3 out of 5. Let's set up our table of knowns and unknowns. So this time that we're looking for then is actually half of the total time that we'll be looking for later. We want to make sure that we are clear about that. But one of our unknowns, unfortunately, is v initial. Okay, so let's just go back to our 4 equations. We've got v final equals v initial plus at. And by the way, I'll give these to you on the exam so that you don't have to look them up. Y is equal to 1/2 times v initial plus v final times t. Y equals v initial t plus 1/2 at squared. V final squared equals v initial squared plus 2ay. Okay, so we're talking about y motion here because we're going up. But you'll notice that if I eliminate all of the equations involving the unknown that's not asked for, and that ends up being the initial velocity, then I've gotten rid of every equation. Okay? And so that is why we call it a special case, because every equation has v naught in it. Okay? And so what we want to do then, if v naught is not known, is solve for it first. Drop everything you're doing and solve for it first. Which, in other words, is the same thing as eliminating all of the equations that have time in it. Okay, so if we get rid of all the equations that have time in it, that leaves us with the last equation. And then we can solve that equation for v naught. And so that's what I'm going to want to do first, is solve this equation for v naught. Then I can go back and choose whichever equation I want to get the time of flight. And so that is the key thing then, if we don't know what v naught is we've got to just drop everything we're doing, solve for it first. So here, v naught squared is 0. The initial squared is what we're solving for, plus 2 times a, which is minus 10 meters per second squared, times y, which is 2 meters. Okay, so this is okay that it's negative because it's going to go over on the other side, and that'll give us a positive value that's equal to V naught squared. Otherwise, you get an imaginary value for V naught, which would be troublesome. V naught squared then is going to be 2 times 10 times 2, or that'll be 40. And V naught will be root 40. Which is 6.32 meters per second. Now that we know what V naught is, we can plug that in and solve any equation we want for the time. So now proudly we move V naught over here to our known column, 6.32 meters per second, and then we can use whatever equation we want of these four to solve for the time. And as I've explained to you before, my personal favorite is equation 1 because it has the least amount of algebraic computation and is the easiest one to solve without making a silly mistake or taking too long to solve. So t then from the first equation is just v final minus v initial over a. I should mention here that you could just plug in numbers and solve for the time. And here I'm taking this extra step to solve for it algebraically. Some of you may not feel comfortable with doing that and may want to just plug the numbers in. But the disadvantage of doing it that way is that when you're checking your work on an exam, you may not want to go through all the trouble of working the whole problem through. Whereas here, if you can just work the algebra through, you've only got one step to check for your final numerical calculation. Make sure that it's right. Okay, so what we've got here then for t is going to be 0 minus v naught, which is 6.32 meters per second, divided by the acceleration, minus 10 meters per second squared. And so that would give us 0.632 seconds. So are we done? No. Don't forget that the total time of flight was what was asked for in the problem, and we chose to do a problem where we went to the peak, which is half of the total time of flight. So therefore, t total is equal to 2 times t to the peak, or 2 times 0.632. And so that would be 1.632, that would be 6.4. So 6 and 6 is 12. 632 is 1.265 seconds.